Dear students, in this lecture we will discuss about metallic crystal structures. First of all, we will discuss the face-centered or cubic or FCC metallic crystal structure. As we know that the crystal structure formed for many metals has unit cell of cubic geometry with atoms located. As you can see that this is the horse sphere model for the face centered cubic, and this one is the reduced sphere model for a better presentation of FCC cubic structure. For this crystal structures which has the atom located at each corner and at each face, that is at the center of each face. Here you can see that at the top face, bottom face, this one face, this one is the atom at front face, and this the atom at face behind this face. And so this is the reduced sphere model, and this is the structure is called as face centered cubic crystal structures. So some of the familiar metals which having these crystal structures are the copper, aluminum, and silver, and gold, etc. Here you can see that so this is the structure which representing the many unit cell, which is the combination of different FCC unit cell. So in FCC crystal structures, here you can see that each corner atom which is shared among 8 unit cells. So each corner atoms contribute 1/8 part to this unit cells, while the atom at the faces, that is the face atoms, are shared among 2 unit cells. So each atom at different faces shared among 2 unit cells and contribute half of its part to this unit cells. So we can say that as one atom to this unit cell will come from the corner atom, as each corner atom which contribute its 1/8 part, and so each corner atoms there are the 8 corner atom, so we can say that 8 multiplied by each corner atom which contribute its 1/8 part. So we can say that there will be only one atom which is coming from the corner atom. And there are the 6 faces atoms, and each face atom shared among the 2 unit cells. So one atom will come from so there will be the 6 face atoms. So from face atoms you can say that there are 6 face atoms. So we can say that from faces each atom which contribute only its half, there will be the 3 atoms which are coming from the face atom. So the total number of unit cells per unit cell will be equal to 4. That is the 3 atoms from the faces and 1 atom from the corner atom. So total number of unit cells will be equal to the 4 unit cells. So, 4 atoms per unit cells. So next thing is to determine that is here we take the horse sphere model, and so we need to define the relation between the cube edge length and its radius, and this is equal to cube edge length, that is a, this one is equal to a, this is equal to 2 or under root 2. Let's as we can say this is the horse sphere model, and this is the front face, and each corner atom which contribute only is 1/8 eighth part. So we take this one is length A, and here we take this length, this one is length A. So if we take this triangle, and so this length is equal to R, and this length is equal to R, and this is the hard sphere, that is the central atom, and it has the radius 2R. So we take this triangle here, we apply the triangle law, and it's equal to A square plus A square, and this is equal to 2R plus R plus R. So this total length is equal to 4R square. So its H length, if we simplify it, and this is equal to 2, this is A square will be equal to 16 R square, and this is equal to 16 R square. By simplifying it, its S length will be equal to A is equal to 2R under root 2. So in the same way, the volume of this unit cell, which is equal to the cube of H length, as we have already calculated, its H length is equal to 2R under root 2. So we take the cube of this H length, 2R under root 2 cube, and this will be equal to 16R cube under root 2. So the volume of this face-centered unit cell will be equal to 16R cube under root 2. So another important parameter is the coordination number, that is the number of nearest neighbor. For the metal, each atom has the same number of nearest neighbor atom or touching atom, which is called as the coordination number. Here for the face-centered cube, which it has the coordination number is equal to 12. It can be confirmed from these structures. Here you can see that okay, take here laser pointer. Here you can see that here the front face atom, which has the 4 nearest neighbor atoms surrounding it from front face, that is this atom has this one nearest neighbor, this nearest neighbor, this one. So it has the 4 atom from front and 4 atom as a nearest neighbor behind this face, that is this one, this one, this one, and this one. So it has the 4 nearest neighbor atom surrounding it, and 4 face atom that are in contact from behind, and 4 other equivalent face atoms residing in the next unit cell. So here will be the next unit cell. So 4 atom of that front face of that next unit cell will be its nearest neighbor. So total number of nearest neighbor atom will be equal to 12. So it is the coordination number which is equal to the nearest neighbor atom for this face center structure is equal to 12. And examples, I have already told you that copper, gold, lead, aluminum, all these structures are face centered cubic crystal structures. Another important factor is called as atomic packing factor, which can be represented by APF. So atomic packing factor, we can define it that like it is the fraction of the solid sphere volume in a unit cell. That is, it tells us how much volume of the unit cell is occupied. That is how much volume is occupied with the atoms which are in the form of spheres. So atomic packing factors is equal to the volume of atoms in the unit cell divided by total unit cell volumes. that is Vs divided by Vc. And so for the FCC crystal structure, Vs is equal to, which is the volume of atoms in the unit cell. If we take the atom in the form of sphere, so volume of the sphere is equal to 4 by 3 pi r cube, as the total number of atoms in the FCC structure is 4. So we multiply this volume by 4. It gives us 16 by 3 pi r cube, which is equal to the volume of all atoms per unit cell. So next is the Vc, that is the total unit cell volume. We have already calculated for the FCC structures. Volume of the unit cells is 16 r cube under root 2. Now putting the value of Vs and Vc, atomic packing factors is equal to 16 by 3 pi r cube divided by 16 r cube under root 2, which is equal to 0.74, which is the atomic packing factor for FCC structures. This is the maximum packing factor possible for the spheres, all having the same diameters. Metals typically have the relatively larger atomic packing factor to maximize the shielding provided by free electron clouds, as we know that the free electrons which forms the cloud are present within the metallic crystal structures. Another important metallic crystal structure is called as the body cubic crystal structures. Here you can see that this is the hot sphere model and this one is the reduced sphere model. And here you can see that there are the atoms at the corner of cube and atom at the center of cube. Again, each corner atom which is shared among 8 unit cells. Here you can see that this is the aggregate of different unit cells within the body-centered cubic crystal structure. This is the body-centered cubic unit cell, and each corner atom which is shared among the 8 unit cell, so it will contribute only its 1 by 8th part. So we can say that the total number of unit cells will be equal to, as there are the 8 corner atom, and each corner atom contribute only its 1 by 8 part. So 1 by 8 into 8 plus there are 1 atom at the center of this cube which totally belongs to this cube. So the total number of unit cells belongs to the body-centered cubic crystal structures is 2. So we can say that number of atoms per unit cell is equal to 2 for body-centered cubic crystal structures. Now another important thing about the body-centered cubic is its relation between its diagonal and its edge length. So here you can see that here this one is edge length which is equal to A, this is another edge length and this is equal to A, and this one is equal to A. So this is the atom which has the radius R, as its contribute only its R, and this one is which is equal to 2R, it has a radius 2R. And then another important thing about this body-centered cubic is this one has the radius R. So this one again, this one edge length which is equal to A. So we can say that edge lengths are equal to R, and this one is the long diagonal side. We say that D which is equal to D is equal to 4R. So total length of diagonal is equal to R plus 2R plus R is equal to 4R. So if we draw a line here and we take this one triangle, and this length is equal to A and this one is equal to A, and we take this length as equal to L, so we can say that L square, which will be equal to A square. Here we can write it like this one, A square plus A square. So this is equal to A square. Okay, if we take the long diagonal side, so this will be equal to here, and this is equal to D, and this one is equal to 4R, and here take this equal to, this side is equal to A. If you take this one triangle and this triangle, we can say that this is equal to, here we can say that D square is equal to D square, which is equal to 4R. So here we can write it like this one, D square is equal to L square plus A square plus A square. So D square, which is equal to 4R, so we're putting the value of D square, which is equal to 4R, so it is 4R square will be equal to L square, which is equal to A square plus A square. So putting the value of L square, A square plus A square plus A square. So this will be equal to 4R square is equal to 3A square. By simplifying it, we get the relation between edge length and diagonal. That is, A is equal to 4R by under root 3. So this is the equal to the lattice parameter for this body diagonal. Now another important parameter for this one is the coordination number. Here you can see that the coordination number for this body centered cubic crystal structure is 8. How it is 8? If we take this body centered atom, it has the 8 nearest neighbor atom at its corner. That is, this one is neighbor, this one is neighbor, this one is this atom and this atom. So there are total number of nearest neighbor atom is equal to 8. So its coordination number is 8. So atomic packing factor for this cubic crystal structure is equal to 0.68%. We can calculate the atomic packing factor for body centered cubic crystal structure in the same way as we calculated for FCC crystal structure, that is dividing the VS, that is the volume of atom in the unit cell, divided by unit cell volume. So it's less than FCC cubic crystal structures, as the FCC is the most close packed structures, and body center, which has the only atom at the center of this cube, it is the less packed structure, so its atomic packing factor is 0.68, which is less than FCC cubic crystal structure. And examples of the metals which have the body centered crystal structures are the chromium, iron, and tin, etc. There are a lot of the number of metals which have the cubic crystal structures, body centered cubic crystal. Another important crystal structure in metals is the hexagonal closed packed structures, which is called as HCP as well. As you can see here, that it consists of two regular hexagon at the top and at the bottom, and there is the atom at the center of each hexagon, and there is an additional plane of 3 atoms between these two hexagons. As this is the closed packed structure, which is aggregate of several hexagonal closed packed structures. So here we see that the number of atoms per unit cell is equal to 6. And as each hexagon atom, each atom in the hexagon which is shared among 6 unit cells, so each atom will contribute its 1 by 6 part. So there are the 6 atoms in each hexagon. So in the top face we have 1 by 6 into 6. So one atom will comes from the hexagon atom, and this central atom and this one which contribute only its half. So there are the two hexagon. So we can say that 1 by 6 into 6, one atom come from this hexagon, and so then at bottom 1 by 6 multiplied by, there are the 6 atoms, one atom will come from this bottom hexagon, plus there are the atom at center of each hexagon which contribute only its half. So there are the 2 atoms at center, one at the top hexagon and one at the bottom of hexagon. So there will be one atom 1 by 2 multiplied by 2. There will be the one atom which is coming from this hexagon, plus there are the 3 atoms which is in the mid plane between the 2 hexagons, which belongs only to this hexagon, plus 3. So there will be the total number of atoms belongs to this hexagonal structure will be equal to 6. So there are the total number of atoms per unit cell will be equal to 6. Another important parameter which is called as coordination number. Coordination number for this hexagonal close path structure or SCP is 12. So each atom in the mid plane which has the 12 nearest neighbor, that is the atom at the corner of each hexagon, at the top hexagon and at the bottom hexagon. So these 12 atoms or its nearest neighbor atom which are touching this atom, each atom in the mid plane. So its coordination number is 12. Then we come to the atomic packing factor. As we know that there are the 6 atoms per unit cell, which is the largest number of atoms in the metallic structure. So it has atomic packing factor which is equal to 0.74%, which is the largest atomic packing factor, and is also equal to the face-centered cubic crystal structure. So it's give it more shielding effect to this metallic crystal structures. So another important parameter is the C by A ratio. That is the ratio of larger to the longer and shorter and short and long unit cell dimensions. And this C by A ratio is equal to 1.633. This ratio also deviates from the ideal value for other metallic structures. So these are the important parameters for the hexagonal close path structures. The example includes the cadmium, magnesium, zinc, and also many other metals which have the SCP crystal structures. Now, another important thing about metallic crystal structure is density computation. That is the knowledge of crystal structure of metallic solid permits us to compute its theoretical density rho through the relationship rho is equal to Na divided by Vc over Na. So here we can define the different parameters related to these structures, like we can define the N, which is the number of atoms associated within the unit cell. That is the number of atoms within unit cell. Here we have the N. For example, in the hexagonal closed path structure, we have the 6 atoms per unit cell. So for SCP, N will be equal to 6, and A, which is atomic weight, and Vc which is the volume of atoms in the unit cell. We can also calculate VC. Then Na, which is Avogadro numbers, and it has its own specific value, which is equal to 6.023 into 10 to the minus power 23 atoms per mole. So this is the formula for the theoretical density computation of different metallic structures. Dear students, in this lecture we will talk about close packed crystal structures. There are many ways to describe the crystal structures, as like we have already discussed in our previous lectures. We can represent them by hot sphere model, by reduced sphere model, and then here we have the closed packed structures. We discuss the closed packed structures. These are the closed packed. So the closed packed structures are those structures in which the atoms are very close to each other. Like we have the atom which have the nucleus like this one, and it has, along with the nucleus, it has electron cloud like this one. So let we have another atom which have the nucleus and it has electron cloud around itself. So now we have another atom in the same sequence and it has electron cloud in this way. So these atoms are very close to each other and these are stacked to each other in this direction. So these atoms are stacked with each other in the form of close packed structure in certain direction. Let we draw an atom here. Like we represent the atom by sphere. So this one is atom, this one is another one, this one is another one, another one. This is one plane of close packed plane of atom onto which we draw another plane of atom like this one, and onto which we can draw another plane of atom. So this is close packed, these are the close packed planes of atom. So atoms are attached with each other in certain sequence. Now we will discuss the different stacking sequence in which these close packed planes are attached with one another. Close packed plane of atom having the A, B, C stacking sequence. Like this one. This is the planes of atom. This one is the plane of atom which having in the stacking sequence is represented by A, and like this one, all these are the atoms with stacking sequence A. In between these planes there are another plane. Here you can see the this one, like here we have the B, and so onto there is another plane of atom, and this plane of atom having the stacking sequence of B. So onto B again, and then there is another stacking sequence attached with this B plane of atom, which is called as C, and this one is the A sequence. So these closely packed planes are attached with one another in certain sequence, and this sequence is A, B and C stacking sequence. Let we have another sequence which is called as A-B stacking sequence for closed packed plane. We have the set of planes represented by sequence A, onto which there is another plane which is represented by sequence B, and then again structure is repeated. We have A stacking sequence, and then onto which there is B, then again there is A and then B. So this is the stacking sequence A B A B A B stacking sequence. So atoms or closely packed atoms are attached with one another with certain sequence. This one is the hexagonal close packed structure, which is also called as HCP. These hexagonal close packed structures have the two types of the plane. The upper plane have the stacking sequence represented by A, and then there is the lower plane having the stacking sequence B, then again A, then B, and then again there are AB. So its stacking sequence is AB and AB. It's repeated and so on. This is the hexagonal unit cell of hexagonal close packed structures. So the plane A can be represented by the atoms like this one. So in the plane A, atoms are attached at the corner of hexagon and at the center of hexagon. So this is the plane A. This is called as A plane. Then there is another additional plane within the hexagonal close packed structure. As we have already discussed, it has 3 additional atoms. So this plane is represented by B. So this is the plane B. Again, there is another hexagon which have the atoms at the corner of hexagon like this one, this one, this one, and this one. So this is again, this is the plane A of atoms. So it has the repeated stacking sequence AB. Like here you can see this is the A, this one is the B, again this is the A, and then if there is another unit cell, then there will be the B, A, B. So in this way, this stacking sequence is repeated in the hexagonal close packed structure. It has the most efficient atomic packing factor, as we have already calculated the atomic packing factor for this structure, and is equal to 0.75%, and it is the most efficient atomic packing factor for metallic crystal structure. This one is another close packed structure which is called as the face centered cubic or FCC structures. It also has the most efficient packing efficiency of 0.75%, which is equal to the hexagonal close packed structure, but its stacking sequence is different than hexagonal close packed structures. It has the plane B of atoms and then A, then C. So its stacking sequence is BAC, and this stacking sequence is repeated throughout the structures like B, A, C, again B, A, and C. So this stacking sequence is repeated in this structure. So this is the, here you can see this one is the aggregates of different unit cell, and the atoms are in the form of hot sphere. For face-centered cubic crystal structure, in order to discuss the atoms in different planes, we have structures, cubic crystal structures like this one. So here the plane A of atoms. For A plane of atoms, the atoms lies like at this corner, then here, it will be here, it will be on the front face and on this face, and then it will lie here. So it forms a triangle like this one. So this is the plane A of atom. This is called as plane A. And for plane B of atoms, it can be represented by like this one. For this plane, atoms lies here on this side, on this face and face which is on the behind, and then it will be here on this side. So it form another triangle like this one. This is the plane, you can say that it's the plane C of atom. And then plane B of atom, the unit cell can be completed by having the plane B of atom which is lies on the A. So the atoms in this unit cells in different planes are arranged in this way. So this it has the stacking sequence B, A and C. So these are arranged in this way. This is the unit cell FCC structure having the stacking of a close packed plane which is B, A, C.